Hi guys, welcome to this set of videos, and what we're going to do is we're going to continue our discussion on points of concurrency in a triangle. But let's start off here with our essential question before we take a look at our point of concurrency for this set of videos. What we're going to do here is we want to take a look at how in the last section we looked at perpendicular bisectors. Now we're going to look at angle bisectors, right? So your essential question is simply this: how can you use an angle bisector to find a point, really important, that is equidistant from all of the sides of the triangle? Let me make a quick clarification here. In the last section, right, the notes that we just did, we looked, right, at the perpendicular bisector, right, where the perpendicular bisectors all met, and it was equidistant from the vertices. Now we're going to be taking a look at a point that is the intersection of angle bisectors, and it will be equidistant from all of the sides of the triangle. Opposite, right? Just the opposite. So here we go. Let's take a look. This is the question you need to be able to answer. How do you answer that essential question? Well, there's several things that you're going to need to know, stuff that we're going to have to go over. Our objectives or learning targets are simply going to be this. You'll need to be able to identify that point that is equidistant from all the sides of the triangle. And once you're able to identify that point, we'll then use its properties essentially to do algebra, to find unknown lengths, just like we've been doing all year here in geometry. So, once again, this idea of a point of concurrency, this is exactly what we talked about in just the last section. Again, I'll highlight the really important part. Point of concurrency is where three or more lines intersect at the same point. In the last section, we looked at the circumcenter, which the circumcenter was the intersection of perpendicular bisectors. The circumcenter was equidistant from all of the vertices of a triangle. What we're going to look at now in this section of notes is what's known as the incenter. We'll talk more about the incenter in a little bit. How do you find it? Intersection of angle bisectors. Once you've found that point of concurrency of the angle bisectors, it will be equidistant from the sides of the triangle, all of the sides of the triangle. And I know at this point, your head's probably spinning with how am I supposed to keep all of this straight? I told you in the last section, hopefully note cards are going to be the fastest way. Kind of make yourself a set of flashcards to help you remember all of this information. You do need to be able to tell these guys apart, know how to find each one, and know the properties of each one. It's just going to take memorizing them, really is what it is. So, intersection of angle bisectors, and the incenter will be equidistant from the sides of a triangle. Now, before we talk about the incenter, I do want to spend some time reviewing angle bisectors with you. We looked at angle bisectors back in chapter 1, but that was a while ago for some of us. So, let's take a quick peek back at angle bisectors. Let me draw you a quick diagram here just real fast. Again, I am freehanding this, so it won't necessarily be drawn to scale, but let's say that I have some angle A, B, C, and I draw an angle bisector. Right, so let's just say, I know it doesn't really look like it, but let's just say that my angle bisector splits A, B, C in half. What does that mean? Well, that means that this angle right here is congruent to that angle right there. That's what bisect means. It splits it in half, splits it into two equal segments. So an angle bisector will split an angle into two congruent angles. Great. What we want to talk about is if I put a point on this line, let's call it point D. How do I find the distance from point D to this ray, BA, or this ray, BC? Well, actually, a really kind of important idea is simply this, because there's lots of different ways that I could draw a line. I could do that one, but I could also do that one, or I could do this one over here, or I could do this one over here, right? If I were to extend A and keep that guy going, right? There's a lot of different ways to figure out the distance from D to that ray AB. I could go to here, 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 or an infinite number of places. What we're going to do is find the shortest distance. What is the shortest distance from point D to this ray BA? I could do it on the other side. What if I wanted the shortest distance from D to this ray down here, BC? Again, there's an infinite number of lines that I could measure. Which one's going to be the shortest? Turns out, the perpendicular bisector. Sorry, I apologize. Perpendicular bisector. That goes back to our circumcenter. A perpendicular line will be the shortest distance. So if you can find a line that is perpendicular to AB and goes to point D, that will be the shortest distance. Same is true for this one down here, right? Whatever line is perpendicular to BC and goes to point D, it will be the shortest distance. Now here's kind of a really important idea. If BD is an angle bisector, meaning these two smaller angles are congruent, what do you think would be true of this distance and this distance? Well, hopefully it should make sense. If BD is an angle bisector, meaning it splits it into two equal angles, then the distance from the angle bisector to each of the sides of the angle should be congruent. Right? They should also be the same. It would make sense, and it makes sense because it turns out that's exactly the way that it works, which is what I've got for you here. So let's run through these real quick. Let me erase this so that I'm not infringing on my theorems here. And here we go. First one, the angle bisector theorem simply says this: if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So here's what they're telling you. In the diagram, please note that they have given you the congruent angles. They're drawn really small in there. Let me make, sorry, that's my highlighter. That's not what I want. If you know you have an angle bisector, meaning you know that those two angles are congruent, then what this theorem tells you, right, is that a point on the bisector will be equidistant from the side. So as long as it's an angle bisector, you know that those two lengths have to be congruent. That's the theorem. So let me real quick just tell you what this is. This is this theorem tells you that AC is congruent to BC, right? A to C is congruent B to C. That's what the theorem tells you, as long as you know right, that it is an angle bisector, that these two angles are congruent. So as long as you know that angle APC is congruent to angle CPB, as long as you know it's an angle bisector, then this theorem tells you that those two lengths have to be congruent. Now, reverse that. Vice versa, we have the converse, which simply says the exact opposite, right? If you know, please look at what they told you. If you know that these two lengths are congruent, look at what they put in there, right? They gave you those little hash marks right there, right? That tells you that these two lengths are congruent. If those two lengths are congruent, then you know this must be an angle bisector. It has to be. So please note that these two theorems are saying the exact same thing, just in reverse order. If you know it's an angle bisector, then these two lengths have to be congruent. This one, if you know these two lengths are congruent, then this must be an angle bisector. So this tells you that angle APC is congruent to angle CPB. You know that these two angles have to be congruent when you're told AC is congruent to BC. So these two theorems are just right. They're converses, right? That's why it's called the converse. They're inverses of each other. Given that the angles are congruent, you know that those two lengths have to be congruent. Given that the two lengths are congruent, then you know it must be an angle bisector. What we'll do on the next page of the notes is take a look at a couple of problems and how we can use these two theorems to figure out unknowns. So head on over to the next page of the notes. I'll meet you guys there.